with joint, say, PDF f x1 x2, and imagine y1 is a linear expression in the terms of x1 and x2. Okay, say y1 is x1 plus x2, okay, and y2 is x1 minus x2 actually. Okay, x1 minus x2. The question is, what is the joint CDF of y1 and y2? Okay, so here's the solution. So first identify the functions. So I have function g of x1 x2 equal to x1 plus x2, and g1 of x1 x2, g2 of x1 x2 is what do you call x1 minus x2. Question is, now what are the h1 h2? So what you can do, whatever the equations are given to you, just solve them in the terms of x actually. In the terms of x, solve them for x in the terms of y. Okay? So what you can do, for example, if you add these two equations, now for finding h1 and h2, what you need to do, you need to do the inversion. And for inversion, you have to write x1 and x2 in the terms of y1 and y2. So if I add these two, for example, the easiest way is y1 plus y2. Okay. y1 plus y2, so it's going to be x1 plus x2 plus x1 minus x2, so it's going to be 2x1. So the x1 is going to be y1 plus y2 upon 2. And if I take the difference of y1 and y2, so it's going to be x1 plus x2 minus x1 plus x2, so it's going to be 2x2, hence x2 will be y1 minus y2 upon 2. Okay. Hence, what does this shows? This shows that my h1, so x1 is function h1, which is function of y1, and y2 is y1 plus y2 upon 2, and x2, which is h2, y1 minus y2 upon, what do you call, 2. So this is what is your, no, h1, that is a function of y1, y2, is a function of y1 minus y2 upon 2. Okay. By the way, here x1 and x2 are two generic functions actually. Okay. Now let's come to the formula. So what would be f y1 y2 evaluated at y1 y2? So take your f x1 x2 and substitute h1, which is y1 plus y2 upon 2, and h2, which is y1 minus y2 upon 2, okay, and multiplied by the Jacobian, reciprocal of the Jacobian. And what would be the Jacobian now? Jacobian is partial g1 by x1, so g1 is this. So the partial derivative of g1 with respect to x1 is going to be 1, and with respect to x2 is going to be 1. With respect to x1 is going to be 1. With respect to x2, this is going to be negative 1 actually. So the final formula that you're going to get is minus 1, 1. So you have minus, okay, minus, there must be, so there is an absolute actually, yes, you can't have, there is an absolute on Jacobian as well. So we need to put an absolute here as well. So this is going to be minus 1/2, so it's going to be 1/2 minus 1 So no, it's going to be minus 2, and absolute of minus 2 is going to be equal to 2, and its reciprocal is going to be 1/2. So it's going to be 1/2 f of f x1 x2 evaluated at y1 plus y2 upon 2 and y1 minus y2 upon 2. This is what is the case. Now, I would like to consider, so this formula that we have derived is a generic formula. Generic formula. In other words, x1 and x2 can have any distribution and any PDF, but y1 and y2 are written in this manner. Okay, then the CDF is going to be this. So if you know the joint CDF of x1 and x2, you know the joint CDF of y1 and y2. So let's do this for two concrete examples. So imagine x1 and x2 are two uniformly distributed random variables and that are independent. So they are independent uniformly distributed random variables. So what would be their joint PDF? So the joint PDF of fx1 x2 of say x1 x2 is going to be the product of the PDF of x1 and the PDF of x2. But what would be the PDF of x1 if it is uniformly distributed? So it's going to be 1 over 1 minus 0, so 1 times 1, when x1 is between 0 and 1 and x2 is also between 0 and 1 actually. Okay? x2 is also between 0 and 1. So fx1 x2 of x1 x2 is this and equal to 0 otherwise. Okay. So now for such x1 and x2, what would be the joint PDF of y1 and y2, where y1 is the sum of two uniformly distributed random variables and y2 is the difference of two uniformly distributed random variables. So this is going to be fy1 y2 at y1 y2 is going to be what? So fx1 x2 is a function that follows anything x1 x2 but gives an answer 1 actually. So what would be the fx1 x2 of y1 plus y2 and y1 minus y2 upon 2? Again 1 actually, because it's a constant function. So it's going to be 1 when y1 and y2 are between 0 and 1. 1 multiplied by 1/2, so this is going to be equal to 1/2. And equal to 0. So the constant are x1, which is equal to y1 plus y2 upon 2. So I must say this must be y1 plus y2 less than or equal to 2 if I multiply by 2. In other words, in this constraint, if I substitute the value of x1, which is y1 plus y2 upon 2, I'm going to get this. And here y1 minus y2 is between 2 actually. So this is the joint PDF of two uniformly distributed, independent uniformly distributed random variables when the y1 is the sum of both and the y2 is the difference of both actually. You can take y1 and y2 to be anything actually. For example, you take say x1 and x2 to be say exponential random variables. Okay, so let's let's take, say, x1 is exponentially distributed with, say, parameter lambda 1, and x2 is exponentially distributed with parameter, say, lambda 2, and let's assume that these are independent as well. Okay, so these are independent. Now what would be the joint PDF of this? Fx1 x2 of x1 x2, so this is going to be equal to, fx1 of x1 times fx2 of x2. Now what is the formula for exponential random variable with the parameter lambda 1? So it's lambda 1 times exponential of minus lambda 1 x1 times, for this is lambda 2, okay, upon 2. Yes, there is going to be 1/2 as well. Lambda 1 and lambda 2 upon 2. Is there going to be 1/2? No, there is no going to be 1/2. And lambda 2, that is exponential of minus lambda 2 x2. This is what that you're going to get, I hope. And what? Where x1 and x2 are greater than or equal to 0. This is what the formula for this is. Now, if in this formula, on the place of x1 you substitute y1 plus y2 upon 2, and so in other words, if I substitute this formula, evaluate this formula here, so f y1 y2 evaluated at y1 y2 is going to be 1/2 these two numbers, so it's going to be lambda 1 lambda 2 times, I can put these exponentials in a single power, minus lambda 1 x1, and x1 is y1 plus y2 upon 2 minus lambda 2 x2 is y1 minus y2 upon 2. So this is what is going to be the joint CDF of two exponentially random variables, where y1 is the sum of two exponential and y2 of the difference of two exponentials actually. And obviously x1 and x2 greater than or equal to 0 means y1 plus y2 is bigger than or equal to 0, and y1 minus y2 are bigger than or equal to 0. So these are the two constraints that it should satisfy. One exercise for you to do the same but for normally distributed random variables. So imagine you have two independent normally distributed random variable with mean mu x and sigma x square, and y maybe x1 is this and x2 is x1 normally distributed with mean x2 and sigma x2 square, and your task is to compute the joint CDF of y1 and y2, where y1 and y2 are these actually. Okay, so I would also say to maybe one exercise for you to do the example. So another exercise for you to, that's a kind of a reading exercise, to read carefully, okay, and make sense of examples 7b and 7c.